Hello. Now, what I would like to show you in the following demo series is how to take this sub-assembly from a motorcycle and determine the forces and optimize the structural part from this suspension assembly. So for that, as mentioned, we'll use the Inspire module, and from Inspire, we'll use the motion module to determine the forces due to the motion of the suspension assembly. We then use the forces to find the optimal layout and optimize the structural pivot part of the suspension. And finally, use the final design of this part to simulate it in a 3D printing simulation, which will be the third part of the demo. So starting why we use simulation at all, or how simulation for design works at all, I would like to give you a small example. So here, for example, is a simulation of a crash event. So it's not a real car, but still you can see there are those Lego figures sitting in the two cars that have then been evaluated with a real crash simulation with Altair in that case, which is giving you the result that you can basically see a very basic design flaw, that is that the Lego figures here didn't have any seatbelt. And using simulation in this sort of validating an existing structure might be useful, but it might also come with a big flaw, because as you could see here, the seatbelt flaw is basically seen in the development process at a very late stage. So basically only after the simulation is done, you'll see that something has been missing, which is of course a very obvious error, but just to give you an idea, those type of, let's say, smaller errors occur regularly. And if you do simulation at a very late stage, you will observe them very late and will not have the time or the capacity or the possibility to even influence your CAD design anymore, because the process is already too late to implement any changes. So therefore, what I would recommend you to do is use simulation upfront before your design. So to use optimization and simulation to determine optimum layout of your structure, and by this basically enabling a more mature and more performant design. Also, if you use simulation at a very early stage, you will realize that the time saving will be enormous, because if you deduct a design from a simulation, it's already validated at a very early stage, and you can basically implement only minor changes at a later stage, or do manufacturing simulation in addition, which then again will lead to also a higher maturity and performance level of your assemblies and parts. Now, this is basically done, for example, with a method called topology optimization. So topology optimization is a means of finding the optimum material distribution and finding the optimum material layout in a given design space. Imagine it like this wooden Jenga tower on the left. So what you do in a topology is you define the maximum possible material that you have available. And from there, you remove variables, basically removing elements, or given on the picture on the left, removing wooden blocks from your structure until you reach a certain goal and a certain constraint. So for example, you define, let's remove here now from this block single elements until you find a minimum weight solution, a minimum mass solution, but still allowed to carry the stresses or to carry the displacements and strains that occur. How is it done? Basically, as mentioned, you define this design variable of your finite element model, which is a so-called density value. The density ranges between 0 and 1. 0 meaning there's no mass and no stiffness left in your element, and 1 meaning the element has full stiffness and full mass. And by varying this virtual density, you can find changing layouts, changing material distributions in your design space, which is the maximum design that you have. And from there, you reduce to the final design. What you need to define, of course, is, as mentioned, a design objective, which is the goal of the optimization. So, for example, make it as light as possible. And what the second thing is you need to define is a constraint. So only telling the software make it light is not enough. You need to define, in addition, an engineering constraint like a stress, a strain, a displacement, or a frequency. All right, now this is implemented in Inspire structures, and what you need, of course, as a basis for the optimization is a finite element model with forces and boundary conditions. And now these boundary conditions can be, for example, determined from either a pre-existing part or from an engineering code. But of course, you can also determine these loads and forces that occur from a simulation, from a so-called multi-body simulation. And that will be the first demo of today, showing you how to use Inspire Motion, which is a multi-body dynamics simulation software, to determine the forces acting on a structure. And from then, in the second demo, we will go from the finite element model with the forces to the optimization model, which includes then the varying design elements, the objective and constraint function for optimization. You will see in the second demo then how the simulation will iteratively find a solution, leading to a final design, which you can then deduct for the CAD and create your design from there. All right, now I will show you this on the suspension example. So the blue part is the one that I would like to optimize. So that's the part that will then be used in the topology optimization. But the first step, as mentioned, is a motion analysis to determine the correct forces for this assembly. And the motion analysis will be the sort of analysis that you see here, which is a rendered simulation result. So in the motion analysis, you basically give the software a dynamic event, a dynamic, for example, road event leading to motion in a structure. You will define the different couplings between the different parts, and from there can deduct the forces acting on the different parts. Okay, now this assembly here is already showing you the animation result, and in the following demo, I will show you within Inspire Motion how to set up this sort of motion multi-body analysis. Okay, so here you see the geometry assembly of the motorcycle suspension without any couplings between the different parts. So if I would start an analysis here, you would basically see the whole geometry falling apart because there is no connections between the different parts, and there is also no ground structure, no damping and spring structures connecting the different parts of the assembly together. Now, to do this in the Inspire suite, there's a dedicated menu called Motion, where you can basically define all the different setups that are needed for this sort of simulation. The first one being defining a ground part. So the ground part is basically the fixed part in the simulation, and the other parts being then, for example, rigid or flexible parts, which are allowed to move either as a rigid group, so basically meaning with different parts grouped together as a solid or rigid entity, and other parts could be defined then as flexible, meaning they can deform during the analysis. To access the menus here, what you need to do in Inspire, it doesn't matter in which menu band you are here, it always is the same procedure. To activate a function, you will then see the mouse cursor activated, which will allow you to select one or multiple parts. And in that case, I defined those two parts to be the ground parts of my simulation, basically meaning that they are fixed to the motorcycle and are not allowed to move during the simulation. Now, every menu, or almost every menu, has again a table next to it, so you can review what you defined in that case, and you will see that those two parts have been defined as the ground parts. All right. Next thing to do here is to end the function. This can be done with the right mouse click, and then start to group the different CAD components together as rigid groups. This is already predefined in this model. You will find 6 rigid groups consisting of different CAD parts, which are here mentioned on the right side, which basically means that all those rigid groups should behave as one rigid part during the multi-body simulation. Now, this rigid group here will later be converted into a flexible group, meaning it is allowed to deform and thus creating strains and stresses on this part. And from there, the second demo will show you how to optimize this pivot here based on the stresses and forces that result from the kinematic analysis that I define now. Okay, as mentioned, every menu can be ended with the right mouse click, so the review of the rigid parts is done in that case, and I can define the so-called joints in my model, which is connecting the different rigid groups together. So the connections can be, for example, ball joints, rotating joints. They can be linear joints, meaning the parts can move in a certain way or with certain degrees of freedom in relation to the attaching or to the next part. Now, if I go to this joints menu, you will see there's a search algorithm which will automatically find all the different either aligned holes or the single holes in your model. And from there, you can review the holes that were found automatically and manually define or select the ones that you want to convert into a, for example, pin or ball joint. Okay, what it found here is first the aligned holes of my structure. You can, for example, zoom in or use the arrows here to isolate the different found holes here, and then click on the ones that were found. Choose a sort of connection, in that case a rotating pin, that should describe the relation of the two parts here, and then go to the next one and for example define the next rotating or other joint. All right, there should be some more. If they are not found automatically, you can still add them manually. So, for example, in this case here, the algorithm didn't find all the different holes that are aligned to each other here. You can either rerun the algorithm, or you can manually, for example, add surfaces here and manually add a grounded pin at this at this location. Then there's a final one here, and by this I have grouped the different parts together through rotating pins. In addition, what you can also find is single holes. So single holes are basically holes that are not aligned to each other, but that are still available in the geometry, for example, to be fixed to the ground. So in that case, I'll define a grounded pin, which means the rotation at this hole is still allowed, but it's fixed in space, so there's no other movement allowed other than the rotation. And same can be done here, which is basically restricting the degrees of freedom in your assembly. All right. Now, the setup would still need some more definitions, like, for example, defining actuator and spring systems if they are in the assembly. And the spring, for example, can be defined by, again, clicking on your geometry parts. For example, going to the center point of this surface here as the first starting point of your spring, then rotating your view a bit and going to the center point of the opposite surface to define a spring here. Now the spring can be defined with certain stiffness and damping values. You can choose also from a spring damper system or spring or damper only, which would mean, for example, damper only, then only the damping factors can be entered. Spring only, only the stiffness will be entered, or spring damper in combination would mean both are available. You can define the dimensions of your spring, which is basically drawing the spring in the correct sizing, for example, with a 50 millimeter diameter, 6 coils, and a wire diameter of 8 millimeters. Okay, now that's the definition of your spring. I will define it as a parallel mount, so it's not allowed to have any other movement on the origin and objective surface here. All right, so this is basically almost everything you need to define for your multi-body dynamic analysis. But what's needed in addition is the actuating forces or displacements on your part. So in that case, there's already an actuator defined. And with this actuator comes a function of, for example, the displacement, where you will define, for example, a displacement of 100 millimeters, either as a single event or as a sine function or as a ramp-up event. So there are different events available, or you can also input user-defined events, for example, like the road, bumpy road event that I showed in the video in the presentation earlier. So in that case, let's stay with the actuator that will create a displacement of 100 millimeters on the selected surface. And from there, we can run and start the multi-body simulation. So to do so, you can go to the analysis settings here, define an end time of how long the simulation event should be, and how many outputs you want to have during the simulation. Now, let's say we want to have simulation of 1 second and an output rate of 30 Hertz. And once this is done, you can click on the Run button and get a result a couple of seconds or minutes later. Now you see the actuator creating the displacement of 100 millimeters, and the resulting forces and displacements can now be read from your simulation result. For example, by clicking on a joint, you'll get the forces acting on this joint, which is now relevant for the structural strain and stress simulation that is about to follow. And you can also have a look at the spring damper forces on your spring element and basically click on every single joint or part in your model to see the resulting forces which act due to the actuation event that we defined. And that's basically the multi-body simulation part. And from there, we'll now go to the second demo, use the force extraction method to create a stress analysis and subsequently an optimization analysis on this pivot part here. Okay, so thanks for joining so far, and hope to see you in the next demo that is now to follow.